Let's talk about the applications of exponential growth. P is the principal. We'll let this represent the amount that you invest. The annual interest rate is R. Note it's annual. If you put $100 in as your principal and you have a 5% interest rate, at the end of 1 year, they'll take $100 and they'll multiply it by 0.05 to give you what? $105. So you have gained $5 for allowing the bank to use your money for 1 year. That's if you're compounding it once per year. So at the end of the year, we'll call this P1 for the end of 1 year. You're going to get the principal you put in plus the principal times the interest rate. So again, if our example was a very simple 100 plus 100 times 5%, well, 5% of 100 is 5, so that'd be 100 plus 5 is 105. Of course, we could simplify this expression, P, the principal, plus principal times rate, by factoring out P. So this would be P times 1 plus R is another way to think of that. So this will be an important concept for us if we're talking about compounding interest. After year 0, our initial input, our balance after compounding will be P. So if you put $100 in, if you don't wait any time, it's still going to be $100. But if you wait 1 year, as we saw, the principal after 1 year will be whatever we put in plus whatever we put in times the interest rate. And if we factor out P, we'll have P times 1 plus R. Well, what gets interesting is if we increase the years to 2. Now, P after 2 years will be whatever we had after 1 year, which is P1 plus P1 times R. So let's just say our principal was $100 and our interest was 5%. So 100 plus 5% of 100 gives us 105. So P1 is 105. In other words, I'm starting now with 105 and 105 instead of my 100 and 100. So I'm already very happy. Things are going well for me. And so if I factor out the P1, then I'm going to get P1 times 1 plus R. Now it's important to see that we know that P1 is equal to P times 1 plus R. So if I substitute for this P1, I'm going to have P2 is equal to, I'm substituting for P1, I know P1 is equal to P times 1 plus R. P times 1 plus R times 1 plus R. This 1 plus R came from here, and this expression was substituted for P1. So you can see P2 is equal to P times 1 plus R squared. Notice this 2 is the same as this 2. I'm not so concerned with 2. I want to know what happens after an indeterminate number of years, almost like when we're doing sequences series. I want the general term. Well, the equivalent of that would be P at some time t would be the original principal times 1 plus R to that. Well, if this was 2, this was 2. If this is t, this is to the t. And that is going to be super important for us. The amount of money in the account after compounding is going to be, t is in years, P subscript t, t is in years, will be the original amount you invest times 1 plus the interest rate, all raised to the number of years you're investing it. Whatever goes here is going to go there. One little tricky issue here is that we don't always compound once per year. So let's let n, this variable, equal the number of times we compound per year, and t be the number of years. So our equation was P of t equals P times 1 plus R to the n. Well, that's a little bit, no, this was t here. That was a little bit simplified. So we're going to change this simplified equation into A for, I think of that as amount in the account is equal to principal, the amount that you invest originally, times 1 plus R divided by n to the nt. Now, again, this is a better equation here because it allows us to account for the fact that n is not necessarily 1. Notice, if n is 1, then we revert to the equation we just derived. But if n is not 1, then we have to put it in. It's better to use this one. Again, this one is principal, the amount you originally invest. R is the interest rate. T is time in years. And n is the number of times you compound per year. So if we say we compound annually, then n is 1. If we say we compound semi-annually, then n would be 2. If you say we're going to compound quarterly, that means 4 times per year. If you say we're going to compound monthly, then n goes to 12. Daily, n is 365. And weekly, n is 52. So I'm going to do a little fancy math for you here. We're considering this amount in your account balance is equal to the original principal plus times 1 plus the interest rate divided by the number of times you compound per year, all raised to the number of times you compound per year times the number of years. So we talked about how n can change. If you're doing it quarterly, that's 4 times per year. So if the interest rate is 12%, you don't get that. If you're doing it quarterly, they're not going to give you a full 12%. You're going to have to divide that rate. 12 divided by 4 gives you 3%. So you don't get to have 12% of your money back every quarter. Of course, they're not going to do that. That would make your money grow outrageously. So if you want to compound more frequently, they're going to chop down the rate. If you're talking about money that you're saving, then you want a high rate. If you're talking about rates of interest on in the housing market, you want to buy a house, of course, you want low rates. So because you want what's good for your bank account. So here's the fancy math footwork. Let M as in Michael equal N divided by R. Look at this equation. I'm going to try to make some substitutions. This is equal to 1 plus 1 over N divided by R. And out here, I've introduced N over R times RT. So let's see, have I changed anything? 1 over N over R, keep change flip, is R over N. So these are the same. And if I cancel these R's, then I have NT. So these are the same. I'm not expecting you to come up with a way to do that. I'm just saying, can you follow what I'm doing? That R over N is the same as 1 over N over R. And N over R times RT is the same as NT. If you follow me there, great. Now I'm going to make a substitution. I know that M is equal to N over R. So the amount in the account is equal to the principal times 1 plus 1 over M to the, well, I know that N over R is M, and I'll bring down the RT. Of course, I could write this as, algebraically, as 1 plus 1 over M to the M, and then raise this to the RT power. Take a power over power, we'll multiply. I have not violated anything. And of course, we know 1 over M to the M, as M gets bigger and bigger and bigger, is Euler's number E. So A is equal to P E to the RT. And this is what happens as we start to compound more and more and more. Every minute, every second, every half second, every quarter second, every tenth of a second. And as soon we're compounding continuously. And this is for CC, continuous compounding. A equals P times E to the RT. So here we have 2 major takeaways. Takeaway 1, formulas for compound interest. After T years, the balance A in an account with principal P an annual interest rate R written in decimal form. Now, what does that mean? A 5% interest rate, if I give you 5%, that's 5 per 100 or 0.05. And we're going to use the decimal. So 5 goes to 0.05 because it's 5%. If you know anything about Romance languages like Spanish, that's 5% or 5% means literally for 100, 5 for every 100. So you know 2 zeros mean move your decimal place back 2 places to give us 0.05. If you're doing n compoundings per year, meaning it is not continuously compounding, the amount in the account, the balance, is equal to the original principal times the quantity 1 plus your decimal rate R divided by the number of times you compound, all raised to the NT. Number of times you compound times the number of years you leave this money in the account. Our second takeaway is this. For continuously compounding, now we started compounding per year, N is 1. Then every half year, N is 2. Then every month, N is 12. Then every day, N is 365. You can see the number of times we compound is getting bigger and bigger and bigger. Eventually, we're going to be compounding every second, and then every half second, and then every quarter of a second, and then every tenth of a second, and then that will be almost indistinguishable from continuously compounding. Now, this is the best bang for your buck. For a given set of variables, you want, that would be the holy grail, to get continuously compounding out of your bank agent. That is, the amount in the account A is equal to the principal times E raised to the RT. Now, this E, remember, is not a variable. It's Euler's number, which is about 2.71828. So that means that we're going to have exponential growth. And we're talking about your money in the account. You can see we want that because exponential growth means, whoop, we're going to go off the charts very quickly. And here they are more beautifully and right next to each other. Compound n times per year, A is equal to P times 1 plus R over n to the NT. Compounded continuously. I'd like that better because it's going to give me more payback for every dollar I put in. A is equal to P times E raised to the RT.